This is question 22 from the GATE 2021 AA paper. In this question, we are given a 16-bit synchronous binary up counter and we are asked to find out what the clock frequency is for this counter, given that a certain combination of its two MSB and MSB minus 1 bits has a frequency of 24 milliseconds. Underneath the title of the question, you will find the NPTEL course or video that is relevant to this topic. So in this question, we are given a 16-bit synchronous binary up counter and are told that it is clocked up with a frequency of f clock. The two most significant bits are odd together to form the output y. We are asked to find out what f clock, to determine what f clock is based on the period of 24 milliseconds that y is periodic with, right? So the idea is that there is a counter of 16 bits, so we'll call this B15, we'll call this B15, B14, right? The MSB and MSB minus 1 bits. This is the MSB bit, this is the MSB minus 1 bit, and then the remaining bits B13:0, right? And there exists a clock frequency, a clock which has a frequency f clock, right? And the idea with the counter is that it starts with an initial value. Let's say, for example, it starts with the value 0000, that is, in the truth table we'll have B15, B14 and B13:0. So let's say it starts with 00 and then 14 bits of 000, right? This is Verilog notation. 14-B means it's a 14-bit binary number, right? Let's say this is what it starts with. The point is that every uptick of the clock, that is, let's say this is, so the clock will look something like that, and each of these activations is an uptick. So this is the zeroth, this is the first uptick, right? The second uptick and so on. So at the zeroth uptick, there is the initial state, let's say in this position, it's all zeros, right? And at the first uptick, we have 14-B001, and then this is at the first uptick. At the second uptick, it becomes 14-B0010 and so forth, right? So this will happen until you reach 14-B all ones, right? It counts up, right? So that's a counter, and these are just the lower 14 bits. You still have the MSB and MSB minus 1 bits, and crucially for the analysis of this problem, what will happen, so quite clearly the count is just the decimal version of this. So the decimal version of this will be 2 power 14 minus 1. So at 2 power 14 minus 1, 2 power 14 minus 1 will be the last one for which you have 00, right? And then you will get 01 with 14-B all zeros, right? So the point is that there are 2 power 14 clock periods, right? There are 2 power 14 clock periods that are involved in changing B14, right? And as you can, so in the same way, 002, 111 will be involved in changing it to it'll stay so it'll stay as 01 for this period, right? And then it'll stay as 10 for the same 2 power 14 cycles, and it will be 1 1 for 2 power 14 cycles. So the whole point is that each of these 2-bit numbers will stay on for 2 power 14 clock periods. And then, so the idea is that B15 and B14 are ORed together to get the output Y, right? And so what will happen is that the output Y, let's now add Y here, and Y will be 0 for all of this, but as soon as any one of them becomes 1, Y will become 1, right? So Y will be 0 for 2 power 14 clock periods, and it will be 1 for 3 into 2 power 14 clock periods, which is what I have given in this truth table here, right? That is the OR of those two, which is equal to Y, is high for 2 power 14 into 3 clock periods. And the whole point is that that remaining high period is what 24 milliseconds is. So 2 power 14 into 3 into t clock, which is the clock period, is equal to 24 milliseconds, from which you can get t clock as 2 power minus 11 milliseconds, and 1 by t clock is f clock, which is 2 power 11 kilohertz, which is 2.048 megahertz. And this is the answer rounded off to the nearest 2 decimal places. So the answer here will be 2.05 megahertz.